definition of continuity. There in definition 4.2 at the top of page 38. And we were using that formal definition of continuity to prove these two properties back on page 37, these theorem 4.3 and theorem 4.4. And these were telling us that the important operations that we can do with functions, real valued functions, functions defined in the real numbers, taking values in the real numbers. The important operations we have are the kind of arithmetic type ones of sums, products, and quotients of functions. And the more kind of abstract or universal operation that you can do with functions, which is composition, applying one function after another, combining two functions, and running one on the output of the other one. These properties were saying that these operations, four operations, if you like, there, that they meshed well with the concept of continuity. They preserved the continuity so that if two functions were continuous, when you added them together or multiplied them together or divided one by the other, if that's a valid operation for those functions, those combinations will still be continuous at a particular point, or if the functions are continuous everywhere, those combinations will be continuous everywhere. And composition of functions preserves continuity as well. If your first function is continuous and the second function is continuous, when you combine them together, and you glue the output of the first one to the input of the second one, and consider them as a whole single function, that whole single function will be continuous as well. And this is good for the concept of continuity, and you're going to see very similar properties when we're looking at differentiation. The operation of differentiating a function fits very well with these properties as well. And you are able to, and we'll look at them, there are various rules, theorems about differentiation that tell you what the derivative of a compound function is in terms of the derivatives of the ingredient functions that go into it, be the compound function made up of a sum, product, quotient, or a composition of those functions. Okay. So that's a quick recap on what we've been doing in the last few lectures. So what we're coming to now is this notion of differentiation. Okay. Now, I think most of you have encountered differentiation before in your previous studies, so you'll be aware of kind of what it is. So we'll go through the definition of what the derivative of a real valued function is, and I think what's going to be different in your encountering of it now is that we are going to give rigorous proofs of the properties of differentiation by making use of what we've built up and accumulated so far about limiting values of functions and what we know about the behavior of limiting processes. Okay. So our proofs of these properties will, they won't be too technical. They won't be technical on the level of the epsilons and deltas that we were dealing with the continuity. We'll kind of prove them or argue about them at a kind of more a kind of level up by just talking about limiting values of combinations of functions. Okay, but the notion of the derivative of a function, well, if we think of a function here, so we've got the black line is the graph of the function f, and we've got the domain of the function f is the horizontal axis, and the codomain, where the values of the function f are living, is in the vertical axis. If we think of the domain of this function as being a time-like variable, so we've got time running in the positive direction to the right there along the horizontal axis, then the notion of the derivative of a function is this idea of capturing the instantaneous rate of change of the function. It's a measure of how much the function is changing at a particular point. Is the function increasing at that point or decreasing at that point? You can see at this example, every value at every value of the argument x past about this point, the function is increasing in value. For some of these earlier values, the function seems to be decreasing. It's getting lower and lower. But there are different rates of increase as well. So at this point labeled A, the function is kind of increasing, but at this function, at this value of the argument x, it's increasing as well, but the graph is much steeper, so it's increasing at a faster rate. Okay. So this notion of quantifying the rate of change of a function is very important in many areas of mathematical modeling and so on, okay? Because we track the values of physical quantities or the aspects of a mathematical model using these functions, and very often the solutions to a problem involve tracking what's happening to the rates of change, finding out when functions are reaching optimum values, either maximums or minimums, and so on. And what effect certain factors have on functions, whether changing certain factors makes a quantity increase or makes it decrease, and so on. Okay? So we want to have a good, rigorous description of all of this. Okay? But what we have to do is talk very carefully about how we go from talking about the change in value of a function, say between 2 points, to talking about the instantaneous rate of change. So we can certainly look at a function like this, and we can see that at the point A, it has a certain value f of a. At the point x, it has a certain value f of x, and we can talk about the change in value between those points. Now, we're kind of losing information if we only talk about the change in value between f of x and f of a. We might be missing a trick if we only ever talked about f of x minus f of a. What's going on here? That's not going to document. Sorry about this. That's the PC. Document camera. No, should be good. Why is it? Sorry. There we go. There we go. That's how much the function has changed. But that's kind of only half the story, because that's how much the value, that's the difference in the values of the function. But what we're losing here is how far apart are the arguments. Because even if the function is increasing very slowly, if you choose your arguments very far apart, you'll detect a large change in value of the function. Or even this function here, which in some parts of it is certainly increasing very fast, if we choose the a and the x very, very close together, we'll only see a tiny difference in value of the function. So this quantity we would call the absolute change in value. But knowing the absolute change in value is only kind of half the story, because we don't necessarily know how close together x and a are. So whether we should regard this change in value as significant or not, we really need to know the difference between x and a. So if we instead think of f of x minus f of a divided by x minus a, this then becomes the relative change in value. The change in value of the function, which is f of x minus f of a, as a proportion of the change in value of the arguments. Okay, so that's a more appropriate measure. Okay, because now a function like this one, and coming over to, this, as you move to the right here, you see this function is increasing very fast. So even if we choose a and x very close together to kind of bring down or minimize the absolute change in value of the function, when we look at the relative change in value, we'll still see quite a large relative change in value. Okay? Because even if x and a are extremely close together, so that f of x and f of a are extremely close together, because the function is increasing quite fast, there'll be a significant relative difference between the value f of x minus f of a and the difference between the arguments x and a. Okay? So the relative change is the appropriate measure of what shall we say, how much the function is changing. Because it's telling us, what the change in value is of the function, which is the numerator, f of x minus f of a, as a proportion of the change in value of the arguments, x minus a. Okay, but as we've written it there, and as we've illustrated it with the diagram, this certainly isn't the instantaneous rate of change. This is tracking how much this function is changing, well, from this point A compared to this point X. Just to reproduce that diagram, you've got something like this. We've got the point A there and the point X there. So this, we can look at the relative change in value, and that's some measure of what the function is doing. But of course, we could change what the function is doing. We could make the function do some quite crazy things down here. Well, and then maybe get back to that. And this quantity here would still be the same. It's just looking at what's happening by just comparing the behavior of the function at the point A and at the point X. It's not sensitive to what's going on in between. So, the function could be doing some quite crazy things in between. So sorry, have you got a question? Yeah. What page? So there were that diagram's on page 38 of the continuity and differentiation handout. Yeah, okay. Now this relative change in value, it's also got a more geometric meaning. It's also what we know of as the gradient of the slope of this line. So this green line here, which is joining these 2 points in the graph, the slope of this line, or the gradient of this green line, or the gradient in geometry terms we think of as the tangent of this angle theta, the angle that line makes with the horizontal axis going in the positive direction, the tangent of that angle, which is the same as if you make any right angle triangle against that line, with the horizontal axis as one of the sides, it's the ratio of the opposite side over the adjacent side of any rectangle. Doesn't matter how big you make the rectangle or how small the triangle, that ratio opposite over adjacent will always be the same. Okay? So they're all similar triangles. Okay. So what we would like to do, what we'd like to capture is not measuring the change in behavior of the function across 2 points, but rather be able to speak of what the function is doing right now or at any particular time. So to talk about the instantaneous rate of change. Well, we can do that by we think of A as being a fixed reference point here. And we're going to let this argument x, so we think of A as being fixed, we're going to let this argument x approach A. Okay, we're going to shoot x back towards A. Okay? And we know what that is. We know how to talk about that. And we can talk about it geometrically or graphically by talking about the graph of the function. So as you think of moving this point x closer and closer to A, so keeping A fixed, this line will change, of course, because you're changing the height and location of this second point. So the slope of the green line is going to change, and it will start doing crazy things. As if we're talking about this function that has these wobbles here, the green line will be going all over the place as you send x, as it rides up and down these curves. But what will happen is, as long as the function is, well, let's just for the moment say, as long as it's smoothly changing and it's continuous function, smoothly changing. The word smooth is a technical mathematical word. It does have a precise definition, but we'll just think of it intuitively at the moment. As long as your function is a smoothly changing function, and as long as it doesn't have any sharp corners, any pointed corners, that green line, as x approaches A, in the limit, so that's something we know about from what we've been talking about so far in this unit. In the limit, the green line, when x is away from A, is going to converge and settle down to, and in the limit, it's going to be approaching this green line here, where the point x has disappeared, because the point x is now converged to the point A. So the point x and the point A are superimposed there in that diagram. So this line is called the tangent line to the graph. Okay, it's the limiting case. It's the limiting case of these green lines up here, where you're joining two different points in the curve. This is called the tangent line, and it's the slope of this curve, of that line, excuse me. It's the slope of that tangent line that is equal to the derivative of the function at that point. Okay. So the slope of the tangent line, which we think of as the slope of the graph of the function at that single point, that's what we call the derivative. Okay. So we have this definition, 4.3. We say that a function is differentiable at the point x equals A if this limit exists. Okay. So what we're taking a limit of there is this f of x minus f of A over x minus A. Okay, so that's the relative change in value of the function, or equivalently, the gradient of the function between the 2 points A and x. We're taking the limit of that quantity as x approaches A. Now, it won't always exist. It won't, not every function is differentiable. We can say functions that are not differentiable. It's always good to see negative examples of things as well as positive examples. Functions that are not differentiable, well, if f is not even continuous, if f is not continuous at A, then that's going to cause a problem. Okay. Because here's a little sketch of a function which isn't continuous at the point A. So here's the point A. You can see the function making a sudden jump. Well, there isn't a uniquely defined limiting value for this quantity, this relative change in value of the function, because so we're thinking about joining the point A and say some other point X. So we have this line here, which is capturing the change in the gradient of that line is the relative change in value between A and a point X over here. But as X approaches A from this side, at least, you see these green lines are going to get steeper and steeper and steeper. And in the limiting case, we're going to be talking about a vertical line, which kind of, in a sense, has gradient infinity. I'll put equals in quotes it's got an infinite gradient. But that's with x approaching a from the right. But, there's no ultimate reason why we have to let x approach a from the right. X could be approaching a from the left. So if you talk about a point x prime over here on the left, so that's the function. So there, the kind of relative change line is this line here. Now, as this x prime approaches a, the limiting case of the line is going to look quite different. So these points here are above x equals a. So the limiting case, the tangent, the kind of one-sided tangent line is going to be quite different. It's going to be that red line. So we've got these two different limiting cases for these relative change lines. So we don't have a unique value for this limit here. It depends on whether x is approaching a from the right or from the left. Okay. So these functions we regard as being non-differentiable at the point a. I mean, you can talk about it, you can talk about a one-sided derivative, but there's two different one-sided derivatives, whether you're approaching the point A from the left or from the right. But this can still happen even if the function is continuous. Functions that are not smooth. So smooth becomes a technical term in maths. People talk about, especially when you're talking about higher dimensional geometry and so on, people talk about smooth manifolds, smooth curves. And smooth things, spaces and curves, are ones without sharp corners. So here's a function, okay, it's smooth everywhere. And the function could be doing other things. This function is smooth everywhere, except it doesn't look smooth at this point. This point A seems to be, it's a sharp point. It's still continuous at A. The function doesn't make any sudden jump in value at this point A. The values that the function is going to as x approaches A from this side, the limiting case is the same as if x approaches A from the right. Okay? So the function is continuous at A. This is continuous at A. But it's not differentiable. And it's not differentiable for kind of the same reason of the previous illustration, because there's two different limits. There's a left-handed limit and a right-handed limit, and they're different for this limiting value of the relative change in value of the function. Coming from the right-hand side, the limiting case seems to be a tangent line like this. And coming from the left-hand side, the limiting case seems to be a very different tangent line. Okay? So you've got very different quantities for the value of this limit, depending on whether you approach the point from the left or from the right. So these functions are awkward. So the function isn't making a sudden jump in value, but you can say that its derivative is making a sudden jump in value. Because the behavior of the function on the left of A is that the function is increasing. And it's increasing at a fair rate as you approach A from the left, but then it instantaneously makes a change in behavior to decreasing. It doesn't do so smoothly. It's not increasing and then slowly decreases the rate of increase, reaches a maximum value, and then slowly starts to change its behavior to decreasing. It's a function that's coming up, it's increasing, and then instantaneously, as you cross the point A, it suddenly changes its behavior to decrease. So what we can say that the function is continuous at A, but the derivative, the quantity which is expressing how much the function is changing, the derivative is not continuous at A. The derivative is not continuous at A. Okay, because to the left of A, the function is increasing, but instantaneously to the right of A, it seems to be decreasing. So those are kind of awkward cases. Those are cases that for which the derivative, as we've explained it up there, strictly speaking, doesn't exist. Although you can be a bit more flexible and talk about left-handed derivatives and right-handed derivatives. But the feeling is, or the thinking is, that for a function which has a graph which is continuously and smoothly changing, then it should have a well-defined derivative at every point. It should have a well-defined tangent line or instantaneous rate of change at every point. Now, there are some different types of notation that are used to refer to the derivative. And they're both in use. I mean, when you look at different books and different sources, you'll see both of these types of notation used. So we're going to make use of both of them in different situations. Some people would take the approach of just sticking strictly to one form of the notation, but I like to change it around a bit because the different notations have different advantages over one another. So we can use this prime, so this apostrophe after the function letter, well, in maths we'd call that a prime. So we read that out as saying f prime in general. Although in this context, the prime, that stroke, apostrophe-like stroke after the function letter, that's indicating the derivative of the function. And we use those primes in other mathematical contexts as well. Very often, if you're talking about an object x, and you want to talk about an object that's kind of related to x, or a specific example of x, or a variant on x, you might refer to the object x prime. Not meaning the derivative, but meaning something kind of which has an association to x. Well, here it's kind of been used in that same spirit. We've got an original function f, and now we've got the derivative of it. So we're going to just indicate that as f prime. Okay? But you would read that out in English. Seeing this here, you would recognize that it's talking about a derivative. So you'd read it as the derivative of f at a. This is saying the derivative of f at the point a is the limit as x approaches a of this relative change in value. The other type of notation then is this df over dx. So this is indicating that we're differentiating the function f with respect to its variable d, and sticking a line beside it and then the subscript x equals a, that indicates that we're talking about the derivative at the point a. Okay. The first type of notation, f prime, has the advantage that it's less cumbersome to write. It doesn't involve sticking a fraction. Typographically, it looks nicer on the page because it doesn't change the height of the line on the page, and it's quicker to write. But an advantage of the other type of notation, df dx, well, df dx, we can separate the two. We can separate the notation like that. So we've got a piece of notation ddx for the process of differentiation. And there we have the original function f, and we think of the process of differentiation applied to the function. So this form of notation allows you to refer to the differentiation operator and see it as an operator or a process that's applied to a function. With the other notation, with the f prime notation, you can't really separate and have a kind of disembodied prime floating. That's not so suitable to talk about the differentiation operator is being represented by a prime on its own. It doesn't really work out nicely like that. Okay. So definitely in situations where we want to stress or we want to talk specifically about the operation of differentiation, in those kind of situations we'll probably default back to this type of notation. But in other situations where we're talking about lots of different functions and their derivatives, or higher order derivatives, sometimes it'll be cleaner to talk about the prime notation. Okay. So let's end by looking at an example or two, taking some relatively straightforward functions. So I'm going to take two functions here, two polynomial type functions. So the first function, f of x, is going to be just simply some constant k times x. So it's a linear function. Its graph would just be a straight line. Straight line of gradient k. Okay. We'll also look at a function g of x, just in linear, but it's the next best thing. Perhaps it's kind of quadratic. So it's a constant k times the quantity x squared. And we can apply the definition of the derivative that we have to these functions, and we can work out directly, without missing out anything, we can work out what the derivatives are. Okay, so the derivative has this formula, the limit of f of x minus f of a over x minus a. Well, we know what we know what the function f is. It's k times x. So f of x is k times x. F of a is k times a. And we want to take its limit. Now, that limit looks awkward because both the numerator and the denominator are both approaching 0. We've got 0 over 0. So that looks like it potentially might cause problems. Of course, we notice that it doesn't really cause problems because there's a common factor, x minus a over x minus a on the top and the bottom, okay? So actually, at everywhere in the limiting process, those two quantities, which are both non-zero, because we're talking about the limiting process. We're letting x approach a. X never actually hits the value a. We're taking the limiting case. So at every possibility x minus a is just a small number, and x, and it's on the top and the bottom, so it just cancels out. So actually, this quantity here is always equal to k. So its limiting value, if it's always equal to k, its limiting value is k. So the derivative of this function k times x at any point is just the quantity k. Now we can do a very similar thing with this function g. So g of x, remember, is k times x squared. There's the definition of what its derivative is, the limit of g of x minus g of a over x minus a. So we look at that there, k times x squared minus k times a squared over x minus a. Again, that looks problematic because both the numerator and the denominator are approaching 0. But again, the x minus a quantity is a common factor in the numerator and denominator, okay? We can factorize the top and see it's k times x squared minus a squared. But x squared minus a squared, a difference of squares, that always factorizes nicely into x minus a times x plus a. So the factor x minus a can be cancelled from the top and the bottom. And we're then just looking at the limit as x approaches a of k times x plus a. Well, that's just a straightforward limit, which we can evaluate by substituting in the limiting value of a into the quantity x. So it's going to be k times a plus a, or in other words, 2 times k times a. So the derivative of this function k times x squared at a point a, we see now is simply 2 times a times the coefficient k. And that argument goes through no matter what the value of a. And in the first case, it also goes through no matter what the value of a. So we'd say that these two functions are differentiable everywhere, differentiable at any real number, and in these results, we can see a formula for the derivative of the. Okay, that just about brings us to the end here. I haven't left you really with many particular problems to look at, but we'll do some work with these in the tutorials as well. And I'll see you next week. Okay.